The divergence theorem states that the sum of the sources and sinks of a vector field F within an enclosed volume, which is represented by the volume integral of the divergence over the region bounded by the surface, is equal to the total flux of a vector field out of a closed surface, which is represented by the surface integral of the vector field over the closed surface. Let us talk now about the first part of this equation, the volume integral. Just keep in mind that the volume is in R3. It is a solid region bounded by the surface S, where it is also equal to dx, dy, and dz. Another thing to remember that there is a scalar product between the nabla operator and the vector field F. The nabla operator has components of partial derivatives, and the divergence measures how much the vector field F flows out or in at a point of infinitely small volume dV. This scalar product results a scalar. The sign of the scalar determines whether there is a source or a sink of vector field F at a specific location in an enclosed surface. If the divergence is positive, the flux is also positive, and thus there is a source of the vector field F flowing out at that point. However, if the divergence is negative, the flux is also negative, and thus there is a sink of the vector field F at the point where the vector field converges. You may ask now, what if the divergence equals to 0? Well, the flux will disappear. This means that either there is no flow at that point, or the flow out is as much as the flow in. Lastly, to know the total outflow or the inflow of the vector field F, the divergence must be summed at every point within the volume V by the volume integral. And that's all what the volume integral of the divergence represents. And now let us jump for the second part of the equation, which is the surface integral. As you can see, ds is the infinitely small surface element of S. Its magnitude is the area of this element. Keep in mind that ds is a vector orthogonal to the surface S. Another thing to pay attention for, we have a scalar product between the vector field F and the orthogonal vector to the surface, which is ds. This scalar product can never be equal to 0, where the vector field F can be represented by the vector F1 and the vector F2, where vector F1 is a parallel vector for the vector ds, and F2 is an outward normal vector for the vector ds. Thus, the scalar product between the vector field F and the vector ds is also equal to the scalar product between the vector F1 and the vector ds. Lastly, all the vector fields of the surface element are summed up by the surface integral. This integral measures the quantity of the vector field F that flows out or in the surface S. In other words, it measures the total flux. As a conclusion, the divergence theorem states that the total flux of a vector field F out or in the enclosed surface S is equal to the sources or sinks of the vector field F at a certain point of that volume. Knowing that the divergence occurs at a point, but the flux occurs across the curve. All this information are extracted from my book Tensor Calculus and the Theory of Relativity.